6 lines of code. That's all it takes. 6 completely reasonable, code review-approved lines scattered across one ordinary checkout handler. And any one of them, alone, can take your API down the moment real traffic hits it. 6 bugs, 6 fixes. All in the same 15 minutes it takes real traffic to find them. Here's how you usually find out the hard way. It's 3 a.m. Your API isn't down. If it were down, the alert would be obvious and you'd know exactly what to look at. It's just slow. Some requests take 10 seconds. Some never come back at all. 10,000 people are trying to check out during a flash sale, refreshing, retrying. Support tickets are piling up. And when you pull up the code, every single line looks fine. Here's the thing nobody tells you when you're learning to build APIs. Almost none of the code that breaks production looks wrong. It compiles, it passes review, it works great on your laptop with one user, you. The bug isn't in the logic. It's in what the logic does when 1,000 people hit it at the same time. The request we're tracing is a checkout. A customer taps Confirm Order. Before your server can say, "You're charged," it has to clear 6 stops. And we're going to follow that exact request, the same handler, the same cart, through every one of them. 6 stops. Each one has a failure mode that looks completely reasonable in a code review and only shows its teeth under real load. Stop 1. Does your server even pick up the request? Node runs your JavaScript on a single thread. One thread, one call stack, one thing happening at a time. That's not a limitation someone forgot to fix. It's the whole design. Node stays fast by never blocking on I/O. It hands a database call or a network request off to the system and moves on to the next piece of work while it waits. But that trick only works if the thing you hand it is actually I/O. Watch what happens when it isn't. Here's the first piece of your checkout handler. Express here, same idea on Fastify or Koa. Build order summary isn't calling a database. It's not waiting on a network, it's just computing, looping over line items, applying tax rules, folding in discounts, building a big object. There's no await in sight because there's nothing to await. It's synchronous, CPU-bound work, and for 2 full seconds it owns the one thread Node has. While that function runs, nothing else on your server runs. Not other customers' checkouts. Not your health check endpoint. Not a callback waiting to fire. The event loop can't get back to the top of its loop to pick up new work until this function returns control. Every other request in flight just waits in line behind it. Here's the part that makes this bug so easy to miss. At low traffic, you'll basically never see it. One checkout every few seconds, a 2-second block barely registers. 10 concurrent shoppers, maybe a little jank. But push that to 1,000 concurrent checkouts, a flash sale, exactly the moment you most need this to work. And that same 2-second block isn't a hiccup anymore. It's a queue that never drains because a new blocking checkout lands before the last one clears. What was invisible in dev reads, in production, as a total outage. The fix isn't a bigger server. A bigger server just means the same block happens to more checkouts at once. The fix is moving the CPU-heavy work off the main thread entirely into a worker threads instance running in parallel. Same 2 seconds of work, it just doesn't happen on the thread your other requests need. The main thread hands off the job, immediately goes back to serving other requests, and picks the result back up when the worker posts it. And notice that error handler. If the worker throws, you still respond, instead of leaving the request hanging forever, which is a whole different bug we're coming back to at stop 6. One rule to take from this. If a function blocks for more than a few milliseconds and it isn't waiting on I/O, it doesn't belong on the main thread. That's stop 1. Assume the checkout request gets picked up cleanly. Now the handler has to actually price everything in the cart. That's stop 2. Your checkout handler needs a live price for every item in the cart. 10 items, 10 independent calls to your pricing service. None of them depend on each other. You'd think that's the easy part. Here's the version almost everyone writes first. This looks fine. It reads top to bottom like a normal loop. It even works. You run it, you get the right total back. The problem is invisible in the output and only visible in the timing. A wait inside a for loop doesn't run those calls together. It runs them one after another. That's not free. It's real wall clock time. Your server holds this request open, doing nothing but waiting on a call that had no reason to block anything else. If each call takes 50 milliseconds, 10 calls don't take 50 milliseconds. They take 500, because item 2's price check can't even start until item 1's is fully finished, and neither of them needed to wait on the other in the first place. You'll rarely notice this on a small cart. Half a second, nobody's timing it. But that's a linear relationship, and a checkout with 50 line items or 1,000 simultaneous checkouts each pricing their own cart turns that same per-call cost into a queue that scales directly with how busy you are. Right when you need speed the most. Promise.all starts every call in the same tick. They all fire together, and the function waits for the slowest one, not the sum of all of them. Same 10 items, roughly 1 call's worth of time instead of 10. One caveat, and it matters. This only applies to work that's genuinely independent. If pricing item 2 actually needed the result of pricing item 1, sequential is correct. That's not this bug. That's just a dependency. The rule, calls that don't depend on each other shouldn't wait on each other. One more thing worth knowing, quickly. Fan 100 or 1,000 of these out to Promise, all at once against a real pricing service and you're not saving time anymore. You're flooding it, which is exactly Stop 6's problem wearing a different hat. The real answer at scale is capping concurrency. Run, say, 20 at a time instead of all of them at once. A library like plimit does exactly that in one line. Worth a search if this turns out to be your bottleneck. Now the handler has its cart priced. Next stop, before any of that pricing math even runs, is there a cache in front of it? And can that cache betray you? Pricing a cart often means checking active promotions. And that's the kind of thing you cache, because it's the same for every single checkout happening right now, not just this one customer's. Compute it once, serve it to everyone for however long it stays valid. The standard pattern is called cache aside, and it looks like this. Read from cache. If it's missing, compute it from the database instead, then write the value back so the next checkout gets the fast path. It looks harmless. It's the textbook version of caching, the one in every tutorial. The bug isn't in this function, it's in what expires in 60 seconds actually means when every checkout in flight is reading the exact same key. That key doesn't expire for one checkout. It expires for all of them at once. Every request reading, promotions, active, was relying on the same 60-second window, and that window closes for everyone simultaneously. Say, during a flash sale, 10,000 checkouts land in roughly the same second that TTL runs out. Every single one of them checks the cache, gets nothing, and falls through to db.compute active promotions, together. The database doesn't see 10,000 requests spread evenly over a minute. It sees 10,000 identical expensive computations arrive in the same instant. This is a cache stampede, sometimes called the thundering herd problem. The very system that was supposed to protect the database from load just synchronized an attack on it. The fix isn't a bigger cache. A bigger cache still expires all at once. It just holds more keys that can each stampede. The fix is a lock. The first request to miss acquires a short-lived lock and is the only one allowed to rebuild the value. Every other request that misses in that window doesn't immediately hit the database on its own. It rechecks the cache a few times, a short wait apiece, because the rebuild almost always lands well within that window. Only after several rechecks come up empty does a request fall through and compute it itself as a last resort. That's not a mathematical guarantee of exactly one database hit. Under an unusually slow rebuild, you could see a few, but it collapses 10,000 simultaneous database calls into a small, bounded number instead of 10,000. A cache that expires all at once isn't protecting your database. It's synchronizing an attack on it. The production-grade version of this, quickly, stale while revalidate. Keep serving last minute's answer a little past its expiry, while one request refreshes it in the background, so nobody ever falls through to an empty cache at all. And if you've got many keys expiring on the same clock, jitter their TTLs so they don't all die on the same tick to begin with. 3 stops down, 3 to go. And you've probably noticed the shape by now. Something looks fine, it isn't. Here's the math. Here's the fix. These 6 bugs share a shape because they share a cause. Code that's correct in isolation and only fails once real load shows up. The next 3 stops push that same idea further. A query that quietly multiplies, a lookup with no shortcut, and a call to someone else's service that can go wrong in a way the first 3 can't. That's part 2, linked below. Subscribe so it shows up when it's live.